Great. Well, I appreciate the chance to talk to everybody today. I almost said this evening. Would love to share with you what we've been working on that we call Quine. It's a streaming graph for modern data pipelines. We'll uncover a little bit more on what that means here in a second. But just quick overview and introduction. So I'm Ryan Wright. I'm the original creator of Quine. This project started 7.5 years ago, somewhere in there. And now it's maintained by a really excellent team of engineers at thatDot, which is where I work as well. The talk for today is really just about the new open source release, where we just released Quine to the world. So we'll talk a little bit about what it is and how it works, a bit about the kind of capabilities that it enables, especially with an eye on the data engineering world. And then I can show you a demo of it running and you can see what it's like to use it. And we'll kind of close with where it fits into data pipelines and enterprise infrastructure. So with that, let's start with this question about what Quine is. And as hinted at a moment ago, Quine is more than one thing. So the word itself, for the purposes of this presentation, it refers to Quine, the streaming graph, which you can see details of at that website, quine.io. But as mentioned before, a Quine is also a program that outputs its own source code. So here's an example, a program that when you run it, it takes no arguments, and the result is a string that is the source code that when compiled will do exactly that. So Quine is a program that outputs its own source code, and Quine, Willard Van Orman, is also a 20th century philosopher for whom both of these things are named. So the name itself goes back to this guy. He was a logician and a philosopher from the 20th century. He actually made a lot of important logical innovations that are kind of the foundation of a lot of computer science right now. So the way compilers work when they're reducing Boolean formulas is based on something called the Quine-McCluskey algorithm. It's a way to reduce and optimize Boolean formulas, and that is attributed to Willard Van Orman Quine. The term referential transparency is another term we owe to Quine. He coined the term functor. So if you're familiar with any of these things, we've got that guy to thank for it. So he died in, I think, 2000. But he's known now as one of the most important philosophers of the 20th century. So our project takes its name from that guy and technically has nothing to do with a program that outputs its own source code. But we have this as a aspirational challenge to write a Quine in Quine and see if we can get Quine to output its own source code in a way other than just going and cloning the GitHub repo. So what is Quine and where does it fit in? It really is aimed at this question of the streaming problem, which with some broad brushstrokes here, the streaming data problem is you start with data on one side and the goal is to turn it into business value, whatever that means to the particular company in question. Take that data in and turn it into business value by interpreting it. That's the middle part. So consuming data and interpreting it and emitting business value, let's write some requirements for this job. So it always happens that it requires high volume of data. We need to process lots of data. We usually need to do it with really low latency. So the purpose of doing it in a streaming fashion is so that we can get answers very, very quickly, not having to wait for big, long, slow batch jobs. And we're going to have to work in a context where there's some limited and usually expensive RAM. So you can't just simply hold everything in memory and put it all together because you're probably working with more data than that. So it usually forces the data engineer into a pattern where you have to settle for time windows to join data together. If you're looking for an A and trying to join it to a B in your data pipeline, then you've only got a limited amount of RAM. So you hold on to A's while waiting for B's, and you hold on to B's because maybe the A's will arrive later. And you have to settle for usually a time window of how much data you can hold on to. But if the A and B that are supposed to be joined together arrive outside of that time window, you're usually out of luck. So that usually forces teams to look harder and think harder and try to turn a database inside out. and take the traditional database style problems and spread them all over their microservice architecture inside their streaming data pipeline, so that they can handle some of the more complicated sides of joining data and holding on to parts and partial matches. And then that forces them to confront all the traditional CAP theorem trade-offs and hard things about distributed transactions. And then what do you do if your processing has to be order dependent, or you need to process data out of order? Well, it raises these questions about data replay, or maybe you need to replay data into a second pipeline set up just for that purpose because you've got to produce an old report for a week ago. Things like this are just a part of the streaming problem that data engineers often have to confront and solve. And it makes this stream processing problem just incredibly complicated and a whole lot to manage. So we tend to walk away with a system that kind of looks like this when it's all said and done. That data comes in and business value comes out, but boy, is that a mess of things to put together. And it takes a lot of people to maintain those systems. It's really complicated to manage. And if we're honest about the different pieces involved, we have some backroom deals about data guarantees that maybe break some contracts, but will work in certain situations. So when it's all said and done, the good news is it is technically possible. We can build these systems. But if you've built these systems, you probably know it's a matter of time before they all go up in flames, and something breaks or new requirements come, and it just drives home the point that these are hard to build and they're error prone, and it's slow and expensive, and it's hard to hire the right people with right skills to build them. And then if a few key people leave, you're probably better off rebuilding the whole thing anyways. But this is kind of the state of the art. I've served on several different teams that have been doing this sort of thing, throughout the last 10 plus years. It's just kind of what you have to do. It tends to be very labor intensive, and the people who work on these systems usually get pretty grumpy pretty quickly. So this was the world we were entering, and we wanted to make a contribution to this space to try to improve this situation and make it a little bit better. So that's where Quine fits in. Quine is a streaming graph interpreter. It's the result of more than 7 years of research and development. We were fortunate enough to be funded by DARPA for most of that time. And so doing this work at Galois with a lot of really excellent other researchers in this space, we were able to focus and spend time to create something that is just genuinely new. And now we've just open sourced it and want to share it. So what is it, and how does it address those requirements for our streaming data problem? Instead of just thinking about high volumes of data, let's pin some numbers to it. We've been able to scale Quine past 1 million events per second. The latency for doing some of the complex processing under the hood has been as fast as about 8,000 nanoseconds. And that's for big, complicated graph queries on a stream of data. More on that here in a moment. Quine doesn't require large amounts of RAM. 500 megabytes is probably fine. We've run it in less. We regularly test it on Raspberry Pis, mostly just for fun. But one of the main capabilities here is that Quine removes the need for time windows, that you don't have to define these artificial boundaries around how and when you can join data together. Instead, just express the logic of what you're trying to do, and Quine handles all the details for you under the hood. And that's part of what we mean by wrap the database back up again, is package this up so that it's easy to deploy. You don't have to be an expert in databases and all the details of that kind of system to use Quine in the data pipeline. Because Quine can take advantage of a little bit of creativity around the CAP theorem, some combination of multiple modes of operation there gives us the ability to stretch some of the traditional limitations. Quine's aimed directly at connecting, at working on connected data. And so that connected data helps us solve a lot of these other messier questions about the order of operations and distributed transactions. So data can arrive out of order or in any order and be put together into the Quine system and get the same answer. And then Quine also has built in the ability to go query past data, just like you query present data. You simply just say, here's a query, go run this and give me the answer. And you get the results of that query applied to the streaming data up to that point. But you can also say, give me the answer as it was 10 minutes ago, or a week ago, or a month ago, and get the results back from that point in time. So we'll get into a bit more of these, but just kind of as a preview of how we approach this streaming problem of turning data into business value. We had pretty high aspirations, high goals of doing something pretty new and novel in this space. But it distills down into two pieces that we really think about, that Quine has these two parts: event-driven data, where it plugs into a Kafka stream or a Kinesis stream and connects to that event stream of data and uses it to build a graph. A graph in the property graph sort of a sense, where it is a data model that is stateful and persistent and relates all the incoming data to all the other data that has been related together. And then the second piece of that is data-driven events. It is really monitoring that graph that gets built for any arbitrary patterns that you want to find, as complex as you like, and immediately, as soon as there's a result, those results stream out to wherever you want them to go. So they could go out to Kafka and Kinesis, and it can be kind of a component in between two Kafka streams, or they can be written to a file or published to Slack or webhooks or any of a bunch of different options there. You can even take those data-driven events and call back into the graph to update the graph with new results.
Hey, Ryan.
Quine, a really powerful kind of computational engine in that respect.
Hey, Ryan, is it okay if I ask a question?
Yeah, please do.
Is that okay, Joe? Is that within the forum? I don't want to violate the forum rules. It's just, is it okay to ask inline questions?
I can't see folks or any of the chat or anything like that. So would love to just have questions asked out loud.
Okay, I'm just going to assume it's good. So in terms of the DARPA, were you guys doing anything with like sensor data? Is that what motivated some of this interest, or?
Yeah, so depends what you mean by sensor data, but the program we were working on was called Transparent Computing. It was a cybersecurity program, and it was aimed at the problem of how to find advanced persistent threats. So an APT in an enterprise environment, they would have gotten into the environment a long time ago. They're lying low and slow. They're extremely sophisticated, so they know how to avoid being detected. And the premise of the program was, if you could collect all the data from all the machines in that enterprise environment at a really low level of detail, like system call level of detail, then you could theoretically stitch it together into a big graph so that you've got a description of what's happening on the whole network, the whole enterprise environment, stitch it together into a big graph and monitor that graph live on the fly. So if you could do that and understand, what's suspicious in that data, then you could find the bad guys and stop them before they escape with the crown jewels. So in that case, the sensor data was instrumentations of operating systems, and then
effectively. So that leads to my other question then. So are you able to time box the growth of the graph, so I can say, hey, I'm really only looking at a graph that takes place within this 24-hour window or something like that? Because so you're able to do that kind of thing, or
yeah, very much so. And that's what a lot of the production use cases will deploy Quine. We'll get into this too. There's the storage layer is swappable in different ways, but a common pattern is Quine gets deployed using something like Cassandra for its low-level data storage, and setting a Cassandra TTL to say, expire data out of the storage layer after 24 hours or something like that, so that it can do its processing statefully, and whatever the time horizon is that you want to store data for, that's the cap on how much disk storage you actually need for the whole thing.
Okay, cool. Thank you.
So a couple particulars around use cases and what it's good for. On the event-driven data side, it addresses some of the data engineering challenges that we were talking about earlier. So high volume data from a streaming source or a batch source or both. You can join lots of streams together. You can handle out of order data because those event streams come in and build the same graph under the hood or inside of Quine. And so even if data arrives out of order, that doesn't matter. It can come in, stream in, build the same graph, and you get the same results. A graph data model gives you that flexibility around not having to know exactly what the data is and what it will be at every point in the future, so that you have some flexibility around the schema and historical queries like we mentioned. But then the use cases that this is being put to really are driven by what kind of patterns you want to monitor the graph for, and what use you'd put those results to. So we've seen applications around cybersecurity in building of new XDR platforms from some of the giant new, the big cybersecurity companies for their new XDR platforms. Graph AI is a topic that we're leaning into pretty significantly for the ability to build on top of Quine, some of these new AI techniques that are just leaving the lab. And we've built one around a new kind of anomaly detection that we call novelty scoring, which I'm happy to show off later on if folks are interested as well. But CDN log monitoring, we've had a number of different use cases for a number of different CDNs of that sort, where stitching their high volume data together so that they can do root cause analysis and understand why certain users are having the experience that they're having, maybe with slow content delivery. Blockchain analysis is another common application, monitoring Kubernetes pods and infrastructure to understand what is happening in your cluster and what just happened, to put those events together into a view of the historical evolution of your Kubernetes system, as well as like data cleansing pipelines even. So just the standalone Quine application to clean data as it flows through and setting patterns and triggers for clean data that then streams out to whatever downstream systems need to consume that for their machine learning purposes or others.
When it comes to many data streams, are you able to address, let's say something comes in at 1 hertz and something comes in at 100 hertz? How are you able to write rule sets around how to join those up? Because the kind of the fidelity of one is much higher than the other. Do you have the ability to kind of manage that issue?
Yes. So the way it works is when defining any ingest stream, you simply just say for every record that is coming in, here's the query that builds that into a graph. And we've got some tools to make that a lot easier, so that if one stream is really high volume and another is low volume, if they're writing to the same graph, they're probably writing different kinds of data. And hooking that data in is really just kind of a semantic expression of what graph are you trying to build from that data. And so the relative frequency of those things becomes largely a non-issue. In fact, I've got in a demo I can show here momentarily, it does exactly that. There's 2 streams and one is much faster than the other.
Okay. I look forward to seeing that. Thanks.
So some of the like kind of a summary of the goal that we're aiming for in that cybersecurity example is a good one, where we're trying to actually produce less data. So a data pipeline takes in a high volume of data, but the goal is to step up the level of abstraction for what that data actually means, and start talking about not just that sensor data at the bottom level about system call this and file that and user this and process that, but actually turn that into meaningful references of a program running, a user logging in, those kind of events. And those events to be interpreted as maybe parts of a stage of an attack in this sort of a use case. So if an attacker comes in, they go through a phase of infiltrating into the machine and then expanding across the network and then exfiltrating data and maybe covering their tracks. So each of those is a stage that is understandable as part of an attack. And so the real goal here, of course, there has to be the obligatory XKCD. The real goal here is to do that data analysis with an eye toward how to reduce the amount of data to make it take a high volume stream of data and turn it into a high value stream of data, where that high value stream is a lot slower, but each item is much more meaningful. So there's less data to process because it's only the data that you want to use.
That's pretty cool.
Yeah. So why don't I pause here, and I'll switch up the order a little bit, and just show you it running to try to give a sense of the intuition and kind of what's involved with this. And then we can dive in and talk a little bit about how it works and how it's able to achieve some things. So there's a URL here if you want to pick up this demo later, but let me run it here just live. This is quine.io, so this is the website. You could go download it for free. It's open source. Here's a GitHub link, so you can go check out the code there if you'd like. But in our case, I'm just going to go to the download here and download the jar itself. As that's downloading, we've built into Quine the ability to use what we call recipes. Recipes are just a pre-configured package of configuration, where it's defined for a particular use case that it is going to go work on a certain kind of data. It's going to do a specific thing to it and produce results of a certain shape. So if I were to go look at, say, this Ethereum tag propagation use case, this is the recipe defined in this longer block down here. There's a little metadata about name and description. But then down here is where it gets into the meat of it. There are two ingest streams defined in this example. The data comes from this URL, and then it uses this query. This is a query in the Cypher language to take every record from that stream and then build it into a graph structure. And then same for the second data stream. So it comes from this URL, and there's a different query to build it into a different structure. And in this example, the first stream is about the blocks that are being validated, and the second stream is about the actual transactions that are moving money around in those blocks. So to run Quine is really just a matter of running this command here. So I'm going to do this on the left-hand side in the console, java-jar. I've got my Quine jar downloaded now. And then at the end of the Java jar command, we just say -r for recipe and the name of the recipe, Ethereum, but I'm going to spell it right. There we go. A little bit of log noise we're in the midst of eliminating. But down here, you can see the, oops, made it too big. See, graph is ready. Application state has been loaded. And it's running this Ethereum tag propagation recipe. So great, we're off to the races, off and running. The data is coming in here from the URLs that we described. There we go. So there's a source of block data and there's a source of transaction data. And what's going to happen is, with the running system here, I can go to localhost 8080, and there's a web UI for exploring the data, for working with the system. This is an empty canvas that will populate here in a moment with some graph nodes that we can look at as they stream in. This is actually, there we go, just updated with a different look and feel. This is some API documentation. So you can create ingest streams through API calls if you'd like. Here we can get existing ones or create new ingest streams using the API. We can set standing queries that watch the graph for certain structures and then stream results out, and a few other things. So the interactive API documentation is built in here, as well as kind of a lightweight system dashboard for watching and monitoring the operation of the system. So how much data is in there, memory usage, how long it takes for some operations, that sort of a thing. But over here in the exploration UI, this is where we can take a look at what's actually in the data. I've got a query kind of canned for pulling out some of the blocks that represent the blockchain data. If I mouse over one of these guys, you'll see just some of their properties. So base fees and gas and all the Ethereum related concepts of what you'd expect in a block being validated. I will, pin them to the canvas so they don't move around on me. If I right click, I can run some queries on each individual node. In this case, I'm going to go look at adjacent nodes. Here we can see some of the graph structure being built. That's the account that mined this block. Down here is a collection of transactions that are in that block. So this had a handful of transactions, including some of them from the same account that mined the block. But if we go look at one of these transactions, you can see it's moving Ethereum measured in Wei from this account to that account. So that graph structure starts to become apparent as we explore the graph here. I can do some other things to find out, just short circuit from an account to another. How is the money sent? If money was sent to another account, we could continue following that chain here. But this is consuming just whatever happens to be live on the blockchain right now. So it's pulling down real Ethereum data, just live as it's being validated, rendering it in the UI, building it in the system behind the scenes. And so far, this is basically kind of like a graph database. You could do this with Neo4j if you really tried. You could just consume data, stream it, build it into a graph. But where this starts to get a bit more interesting is with that notion of standing queries. So we looked at the two ingest streams really quickly, but down here is the second section of a recipe, setting a standing query to actually monitor the graph for a certain purpose to do something with it. And in this case, this standing query is actually going to help propagate tags behind the scenes. So we're going to watch for certain patterns in the graph where the pattern is our ability to come into an account and say, this account is one I'm suspicious of. I think they got their money by illicit means, and I'm going to right click and mark it as tainted. And when I mark it as tainted, a couple things happen. In the UI, we can see these are now color-coded. The one that is tainted with 0 has a new property that says as much, tainted 0, and it's colored pink. Any account that received money from that account has a tainted value as well, and that tainted value counts how far away it is from the original account. So 1 for this first red account down here, 2 for this next red account. And if you look on the left-hand side, there's been some things flying by. There's some more. And what's flying by over there are every instance of an account receiving this tainted money from the first original account. So as money is moving through the blockchain, every account that receives the tainted cash gets tainted itself. And so if we were to go explore that graph behind the scenes, we would find other accounts, maybe further than just a couple hops, that are receiving the tainted money. This is a nice chain to follow here. And again, this is just whatever's live on the Ethereum blockchain right now. So this is how the money is moving from that original account into all these other accounts, just as we're talking. And every time there's a new account receiving those tainted funds, what you see on the left-hand side is a new log statement saying that we found a new match for a tainted account. So every new tainted account gets reported here. We have an ID that tells us where in the graph to go look at it. We have what is its new tainted level. So how far away is it from that original account? These are 4 hops away. Here's one that's 5 hops away. Here's one that's 2 hops away. So that data gets logged out to the console because that's what we asked it to do in the recipe. So the standing query watches for those tainted values, checks to make sure that it's in a validated block. So it uses some of the rest of the graph structure, and then says, go ahead and propagate that tainted tag to anybody who receives the tainted money, and then print to standard out.
So how do you save the results of this? Where is it stored so I can interrogate it later? Is there a place that it's being persisted, or is that up to you?
Yeah, so there's a couple answers. So on one hand, you could direct the output to somewhere stateful. We actually do some of that in the graph here, in that each of these nodes in the graph is saved in the underlying data storage layer. And so all of these tainted values, they're getting computed in real time, but they're also being saved on each of the individual nodes. So they're available for future computation or to come look up later at any point in time that you'd like. And the other answer is you can stream them out to any other system that you'd like. You could publish them to Slack and they'd be persisted there for humans to look at. You could stream them out to other data sources, to Kafka or any downstream consumer that might persist them or do something with them.
Yeah, I was just thinking like in a large problem set, right? You know, where I've got millions of records coming through constantly. Yep. I'd like to be able to persist these in a graph and then like use some, Tinkerpop type thing or something on top of it, yep. Right? And so that's yep. what I'm, because basically you've created some decorations on data based upon your rule sets that you could then later go back and say, hey, I'm interested in all the, like you said, the tainted records, and show yep. me how to relate to Bob, because I have a Bob somewhere else in my, Bob yep. or something. Is that
exactly
fair? Okay.
Yeah. Hey Ryan, associated question. So it seems that you can propagate these properties and do some manipulations, like add one to them. Do you have to worry about like feedback loops and stuff like that?
In truth, yes. So with great power comes great responsibility. Yeah. I mentioned when you call back into the graph to take a match and do something with that match, you could just stream that out and send it to the next system. But when you call back into the graph to mutate the graph and change it, it has the potential that you could change it to make a new match for another standing query. And so that becomes very powerful very quickly. And that's actually how we've seen some of the cybersecurity users kind of walk up that pyramid that I showed earlier, where there's low-level data at the bottom and they start building it into more and more meaningful things in their problem space. But yes, it means that in that process, it is possible to do something like, create a structure, delete a structure, create a structure, delete a structure, fall into some kind of infinite loop that you probably didn't intend.
Can you affect the result, the rules on the fly? Because let's say I have it running and I have an AI looking at it, and I'm like, oh, here's another rule I'd like to inject. So that's on the fly, okay.
Yeah, you can. When you can issue standing queries live to the system while it's running. And if you create a new standing query, there's another API endpoint that lets you control how that gets propagated. So issuing a new standing query to an existing stream, by default, the standing query will be applied to new data that streams in. But if you'd like, you can say, go ahead and also apply it to all nodes that are in memory right now, or to all nodes, including everything that is saved to disk. So they're just different options available for different kinds of use cases.
Oh, okay. That's okay. So you can do either or. Okay, great. Thanks.
So, and then the last thing in a recipe, there's some other things to just kind of change the node appearance or set some quick queries to make it easy to explore around, just some ways to customize the look and feel of that UI we were looking at. But the UI and the exploration here is really meant primarily for just test cases and small samples, but Quine itself is made for very large, high volume data cases. So Ethereum is actually a pretty slow stream of data. And so related to the question earlier, these are the two data streams that are running. We've had 43 on one and 1700 on another. So it's not a very high volume data stream, and they're not synchronized. So one is very slow, the other's faster. But as data streams in, you can explore some subgraphs or some subset of the data here in the UI, but the real work is happening behind the scenes in the backend system, where it's propagating for all the accounts and all the transactions that are being made behind the scenes.
Okay, cool. Oh, that's good.
So a little bit on how Quine works. You may recognize a few pieces of this already, but the graph data model is at the heart of what we're doing with Quine. And the reason is because a graph is more expressive than a table or tree. And tables and trees are traditional data systems. So relational databases store their data in tables. Document stores like MongoDB, or even just working with JSON data as tree structured data. But a graph can represent all that same data and do so without having to simulate the graph with additional processing. So by simulate the graph, I mean, you can take a relational database, store your data in it, and then essentially work with it like it's a graph, joining between tables, following foreign keys to other tables. And you can simulate a graph with some additional processing on top of a table. But the value of a graph is actually that you don't have to simulate it. You get to represent the graph directly, and the extra processing you'd have to spend to simulate a graph can actually be used to make the graph more efficient than it would be otherwise. And so one of the big insights in our research over the last 7 years on this project has been that when having that graph structure available during the streaming process is really the linchpin for being able to improve on what has been graph's Achilles heel. So graph data has known to be kind of slow and good for toy problems, but not really possible in a high volume streaming context. And the reason is because that graph structure hasn't been available during the computation. The graph exists on disk if you're using a graph database. But what's different about Quine is that Quine is a streaming graph. The graph is in memory. That structure is available during the streaming process, and the ideal moment for doing that computation when it is cheapest and most effective to do so. So the graph data model lives at the heart of everything that we're doing and gives us a superset for representing every other kind of data. The graph itself is really analogous to natural language in that a node-edge-node pattern is directly related to a subject-predicate-object pattern from the English language. That graph data model for how Quine works here is paired with a graph computational model. Every node that we looked at gets backed by an actor behind the scenes. So the actor model is this old idea from the 1970s. Carl Hewitt introduced it 50 years ago. And the basic idea is that an actor is a single-threaded little unit of computation that encapsulates state and only communicates with the outside world by message passing. For an actor to send a message to another actor, that's how a query is run. That's also when data is ingested, that's how that data flows through the graph. This is also how standing queries monitor that graph for its shape and for those queries that get expressed on the graph. It pushes it from actor to actor, and each actor does just a little bit of computation to evaluate its portion of the query. So overall, that gives us the ability to distribute a system like this over any number of machines across clusters of any size, and to scale up and use all the available resources on each of those machines so that we can run multi-threaded in high volume situations, taking advantage of however many CPUs are available, however much RAM is available, and being able to scale it to any throughput by just adding more machines to the cluster. The underlying data storage model is what makes this work. We implement an event sourcing model. So where data comes into a particular node, for example, and that node says, I need to save a property, foo is now equal to bar. So in memory, we have the whole node with all of its properties and all of its edges. But the data that is actually stored on disk is only the event source deltas that get added to an append-only log under the hood. And so that append-only log and saving only the deltas makes the system durable and reliable in that fashion, but also very fast because it only has to write small amounts of data and it only has to append them to an existing log. The data storage layer itself is swappable. So it's backed by Cassandra or RocksDB or any of several different kinds of technologies. And so by default, if you just download and run Quine on your own, it'll use RocksDB for storing locally. But with one configuration option, you can point it to something like Cassandra and run a whole Cassandra cluster to achieve high availability and resilience and failover, like good failover characteristics for running in production. So these are some established known ideas in the space, from event sourcing to the graph data model and the 50-year-old actor model. We built on top of this to try to do something different. And as I mentioned, we've been working on this for a long time, for more than 7 years now. And that 7 years really gave us the opportunity to, instead of following the same path that everybody takes in traditional data-intensive systems, we could start from a new location, cover a lot of the same territory, a lot of the same fundamental questions and fundamental issues that you have to resolve when making a data-intensive application like this. Things about consistency and cap theorem trade-offs and transactions and all sorts of questions like that. But we get to solve them in new ways with new capabilities, because as we cover that same landscape from a different direction, we have different trade-offs and can deploy them in different ways. So for us, what that really means is just a couple of the design assumptions for how Quine is built is that we assume that it needs to be stateful to solve some of the challenges that we talked about earlier, but also that it's going to be an infinite stream of data. So data doesn't stop. It's not going to end. It's probably not even going to slow down. It's going to speed up. And so data is going to keep coming forever. And so some of the things we talked about earlier about TTLs and expiring data out so that you're using and working with data that is recent but stateful, and also as long of a time period as you want. Those are some of the design assumptions that we brought to the table for what just needs to be here. Second is this philosophy that all nodes in the graph exist. It's kind of a cheeky inside joke a little bit. You don't have to create a node in the graph. Every node exists. It just doesn't have an interesting history saved for that node. And so you don't have to create a node first and then start saving properties in it. Instead, you just save a property on a node, or you just create an edge between that node and this node. So the creation of the containers of data is just something we get to take for granted. It's just everywhere. They all exist. And what we're doing as we stream data in is we're starting to create an interesting history for each of them. So Quine allows any type of data to be the ID of a node. So a node is primarily defined by its ID. And so if you're going to refer to a node and go query data from it, you can use any type that you like for its ID. So UUIDs or longs or anything you like, even custom classes. You can bake in anything you like into the definition of a node's ID. And then we've created some tools like ID from for how to go find data out of the system. It's an interesting challenge in that if you're going to assume infinite data, well, you can't build an index for an infinite amount of data. So how do you access and find the data that you're looking for? ID from is essentially this consistent hashing approach that lets us use values in the data to generate an ID in a consistent way so that we know exactly where to go find that data and use it in queries. And so then lastly, this gives us some new kinds of capabilities. It's maybe buried the lead, but what we've been doing this whole time is running graph queries on a real-time stream. So data continues to stream through, and you can run arbitrary queries on that stream and the graph that gets materialized from it. So the query languages that we support are primarily Cypher, but we do support a subset of the Gremlin query language from Tinkerpop. So that you could go query some data out using Gremlin queries as well. But graph queries on real-time streams is kind of the first bit. I hinted at this earlier. You can also say the same query that you'd run for the present moment, just add a timestamp, and you can go get what the data used to be at that historical moment. And then standing queries give us the ability to really query the future. So you issue a query, and that query then gets dropped into the graph, stays resident and lives inside of the graph, automatically moving through, being pushed to the next nodes as it becomes relevant, as the data changes. And it watches the data on your behalf, so that when the pattern that you're looking for finally moves through this iteration from left to right to say, the pieces are being created, as soon as they're all there, you instantly get a match and you can take action based on that match. And so past, present, and future are all accessible with queries on the graph. And that gives us the ability to finally banish this artificial notion of time windows for joining data in a stream only if the data arrives within some arbitrary time window. So, excuse me. So the question now, where does this fit into to a modern data pipeline? We see Quine being used in a lot of different ways, but it's basically wherever there's some custom business logic, and it's usually lots of microservices that get built to implement some of this custom business logic. Wherever there's one of those red circles, that might be a good place to use Quine as a way to implement that custom business logic in this stateful real-time fashion. So to integrate Quine into an existing pipeline can be this gradual incremental process. We hinted earlier that it integrates through a lot of existing tools like Kafka and Kinesis. You could use named pipes if you'd like to stream data in. You can feed data in through a REST API, though it's really meant for a more streaming fashion. But really, wherever is the sensible spot in the data pipeline, whether it's new or it's a component being replaced, Quine is meant to be an easy and gradual way to hook in and add value and hopefully save you a lot of time and effort. And just to reiterate, using Quine is this two-sided process. So event-driven data, where event streams have their events built into a graph. That graph is stateful, it is flexible, and doesn't require the schema to be built ahead of time. But then you can monitor that graph with data-driven events. So the shape of the data is what causes downstream events to flow out. And so monitoring that graph for the patterns that are relevant to your application in your particular use case, whatever they might be, and then just saying every time there's an occurrence of that pattern, here's what I want to do with it, and send the data out to this next system. So overall, Quine is aimed at interpreting this high volume data and turning high volume data into high value data. You should be able to find docs and everything at quine.io. And hopefully you download it and give it a try and give us some feedback. There's a Slack community for Quine, including the engineers who built it. So if you have any questions, want to pop into that Slack channel and ask any questions, or ask about use cases or anything particular to your application, you'll find a bunch of the smart folks who helped build it available there as well. And the code is up on GitHub. So if you'd like to take a look, try it out, compile it, add contributions, we'd love to have it. And as we mentioned before, we are hiring as well. So thatDot is the company behind Quine. They're supporting use of Quine in high volume cases in the enterprise. And if any of these things are of interest to you and you'd like to dive into the code as part of the team, we'd love to talk to you. And with that, I'll say thanks.
Cool. Thanks, Ryan. That was awesome. A round of applause for Ryan. Yay. That was great. What questions do you have for him? I know that you already asked a few, but I'm sure there might be more.
I have a question actually about these standing queries. So is it fair to say then that these sort of partial query result stages accumulate in nodes over time? Yes. And so if you say cancel a standing query, do you have like, I guess, some sort of processes that reap, that purge as, once in a while, or just constantly walk the graph, if you will, to kind of clean up after these partial obsolete results. Those I was kind of curious about the sort of that behind the scenes crawling of the graph that might happen there.
Yeah, you've got exactly the right idea. That partial results or partial matches do get saved together with nodes. They get saved in the underlying persistence layer in a way that is easy for us to then clean out in one fell swoop. So if you come in and say, I'm done with this standing query, just cancel it, then it stops the propagation of results. And in the persistence layer, it just clears out that table to recover disk space and eliminate that guy from from just future, like being there in the future.
Gotcha. Thanks.
And do you have any use cases, or has anybody looked at this? Because some of the problems we tend to look at are bandwidth limited use cases. So in a federated model, putting some of this out, let's call them edge nodes, and the idea, because you had that graph or chart earlier about only propagating high value information versus high volume or something. So do you have anybody actually following that from a federated perspective today, or is that just still at the enterprise level is how it's being used?
So there are some very big users of Quine who have high volume cases that they use the enterprise version of Quine, which includes some extra features and functionality around like resilient clustering for lots of Quine nodes all participating together to make one big graph and distributing the load across all of those nodes so that they can reach things like 1 million events per second. So those kind of use cases are relatively common from our perspective, for the larger enterprise companies of that sort. Federated use cases, so like a bunch of individual Quine nodes, maybe on the edge, something we've talked about with more than one CDN company, where they're trying to put some applications like on the edge of their network, and they're kind of approaching it from that federated standpoint. We haven't gone far enough in those conversations to actually give you a good perspective on that, though.
Okay. Thank you. Sorry, my cat.
Yeah, no worries. Didn't think that was you.
Just a question on the query language. So, is it just richer semantically than something like SQL? Just curious, because in this context, especially with this notion of partial results potentially being available, does it support this notion, for instance, of I'm potentially happy with like a partial result and eventual consistency or whatnot? I just wonder if it's more those query languages that you described, are more conducive to that notion, especially again given this fluid notion of there might be data that we're still waiting for, right? That hasn't trickled through yet. So is it just richer semantically to allow those kinds of things to be expressed?
Cypher it's trying to be SQL-ish, but I'm trying to pull up just kind of a little visualization of some Cypher here. So here's a Cypher query. It's trying to be like SQL or kind of thematically similar to SQL. Instead of select, you've got this match statement. But it is more directly aimed at the graph structure instead of the table structure. And so you see some things like this section here. This always amuses me a little bit because it's basically ASCII art. This is drawing a picture of a node. This first node is minor account. And then this is an edge right here. So an edge pointing from the node on the right, the BLK node on the right, to the minor account node with an edge named mined by. And so it's basically drawing in text a picture of a little subgraph here. And then this is extending that node that's in the center of this pattern up here, drawing another edge kind of coming down from it. So in terms of the query language, it is directly meant to work with a graph. And so it's SQL inspired, but it is not exactly SQL. and it is meant to express graph patterns and work with graph patterns. I'm not sure about the second part of your question about how that leads to something like eventual consistency or something like that.
Oh, I was thinking, partial results, given that there might not be a particular property yet available in a particular node, but you might still want to already have like it's called a preview. I just wonder if that even is a use case that people are interested in. I mean, given again, this nature of, data trickling in potentially out of order or whatnot, right? So
yeah, interesting. That's not something we've considered before. So it is part of how standing queries work. So in that under the hood, they do cache partial results, and they're kind of in the process of working toward a full match. And so in that respect, you probably could log something about that, or even alert some data out for partial matches, but we don't currently do anything like that.
Got kind of a follow-on question here. Fitz asked, did you go with a cipher because it's well known enough by graph database practitioners? Yep,
that's exactly why. And because the Open Cipher project was available. We actually we support a subset of Gremlin as well. So we wrote our own Gremlin parser. And so if you want to, you could type cipher in this query box, or you could do something like g.v limit 5, and then just run a query that is a Gremlin query up here. So we don't support the full Gremlin language. Gremlin, just quietly, Gremlin's kind of a terrible language. It's good for like linear path traversals, but it's very hard to use in other contexts, and it embeds the entire Groovy language in the Gremlin language. So it tends to be very slow and hard to parse and unsafe. But yeah, so we support a subset of Gremlin. We support all of Cipher with only a couple little exceptions. I think they're noted on our documentation page. And then we also have a custom language internal to our system that we haven't actually released as open source the capabilities for this yet, just because we don't quite know how to explain it to folks yet. But it's a DSL for turning classes into queries on a graph. So Quine is written in Scala, and you could write a Scala class and of any depth, any complexity that you like. Just write a class and say, find me instances of this class that are in the graph. And it will return a set of typed results that are like hydrated with data from the graph and instances of whatever your custom type is.
I have a question while we're on the topic of these queries. These queries look pretty complex. And so I'm wondering, what's the best way to test those queries? Is it possible to run Quine in memory and use it in unit tests and stuff like that?
Yep, very much so.
Simulate it. Okay.
Yep. So you can run Quine. This should be in the docs too, I believe. But Quine has a number of different persistence components. Let's see here. So, we should add. All right, it'll be in the reference config. Surely it must be. So there's different persistence components here: RocksDB, Cassandra, MapDB, stuff like that we talked about. But also there's more than on this list. Whoops, that's recipe reference. The configuration reference should have not that. There we go. So these are store types. So some different options. Here's the MapDB one that showed up on the docs. There's also an in-memory persister. So it's everything like the data storage is basically just simulated with in-memory maps. And then there's even an empty persister. So if you just want to immediately throw away all data attempting to be stored, you could just say the persistence type is empty. And it'll still have the in-memory cache of those things, but not actually save anything at all to either memory or disk for any long-term storage.
Excellent. And given the complexity of these languages, do you have, is there any, have you seen any successful usage of this by non-technical usage by non-technical users for, say, exploratory analysis. Like, for example, Elasticsearch is kind of pushing it a little bit, but even non-technical users can grasp Elasticsearch API. But this feels kind of, it pushes it a little too far.
Yeah, where we have seen some non-technical users use it is here in the UI. So we have thatDot has a customer who's using this in like for their support team. So they get a call from someone, and they need to go look up some relevant data, graph structured data that is being built behind the scenes by some technical folks who have set it up to build the graph and to monitor the graph for certain patterns. But when monitored or when needed on demand, the non-technical users click a link and that takes them to a page like this. In the
bookmarkable query.
Yep. Yeah. Which I should also mention, it's if you can add a query to a URL. Sorry, Zoom is getting in my way. There we go. You can say localhost 8080. So here's just my running instance, and then something like g.v limit. It's probably hard for anybody to read. Apologies. Limit 10. So all I did here is just say, go to the exploration UI, and then after the fragment, the URL fragment, the hash sign, just include your query after that. And that query will be loaded when the page loads. And so it's useful for things like this. When you have a result, you can take your result and put everything that you need into a clickable query that someone could then just click on and go open and explore and see, oh, it was this transaction. I'm just making this up, right? But it was this transaction on the fly. And then from here, a non-technical user can right click and choose from the selected exploration options that have been crafted for them. So they can be context sensitive. These are, I right click to this account. And so this example is set up with things specific to accounts, like outgoing transactions or incoming transactions. A block or other structures, other types have different contextual options available to them. And so the exploration UI can be customized for those purposes as well. And we've seen that for that much of it to be used by non-technical users as they hunt down the result for some human explanation about some kind of alert that they got from a thing like on the left side of the screen here.
That's cool. Thanks. I have a slightly different question about swappable data stores. You mentioned that the Quine supports S3. And it's very appealing to run on S3, cost efficient and stuff. What are the drawbacks of running it on S3?
Yeah, so S3 support is still experimental in that respect because there are some notable drawbacks. Let's see, we mentioned that Quine, when it saves its data, does so in this event-sourced fashion. And then it takes snapshots as optimizations along the way. When saving data into S3, it only saves the snapshots. And so, S3 as an object store isn't going to function very well, or you won't be happy with your bill if it is continually saving every single update to every single node in the graph. And so the middle ground that we've struck with that particular persistor is to save the snapshots only. So a node gets built, does its work in memory, and then when it falls out of memory, it saves its snapshot at that moment in time. And so that would save its data into S3. But in that case, you run the risk of, if the system crashes after it has done some work to build some context on the node, but before it has expired that node out of the cache to save it to S3, then you would have lost that data.
Do you store that snapshot separate from the write-ahead log?
Yes.
Which means that you can still replay the write-ahead log even in case of that failure?
Yeah, the S3 persistor currently supports only snapshots, though. So it doesn't support saving the write-ahead log style of data persistence. So,
Okay,
but it
thank
is,
you.
yeah, it is part of the open source code. And so if you have a use case and interest in contributing and helping it make something that fits your use case better, that would be an awesome contribution.
Fitz asks also, are other offerings in AWS candidates to help with that? Maybe a Dynamo. He also is not familiar with how Cassandra works.
The question is about other persistence types.
That's what I believe the question is. Yeah, in AWS. Yep.
Yeah, we support several that you'll find listed in the docs here under components and persisters. So we support these 4 really, plus the two in-memory or empty ones that I mentioned from the config. We support these right now, and the S3 support is still experimental. There is support for other persisters. For example, we support, I don't know if you guys are familiar with hydraulics, but this is a, there we go. This is kind of an emerging time series database that has a lot of performance efficiencies, a lot of cost savings for time series use cases, that sort of thing. We support hydraulics as a persistence backend. And there are a couple others that are also supported, or that are implemented, but not necessarily supported. So like LMDB, the Lightning database. Yeah. Hopefully that answered the question. Tell me if not.
So Ryan, what are the big things on your roadmap? Is there anything?
You know, Ryan's got a yeah. Just I'll make sure some of the team is there.
Big things on the roadmap. So right now we're focused on the open source release that we just published recently. And so trying to help folks learn about it, use it, apply it to their different use case. We have features teed up for, I'm trying to remember just kind of what's on the roadmap relevant to that question. Supernodes are an interesting feature of graphs. You know, a supernode in a graph is one node that has, maybe millions of edges. They represent some fundamental computational complexity, but we have some interesting capabilities for what we can actually do to mitigate that. And so that kind of capability to mitigate the effect of supernodes when running a very large scale graph is one of the things coming down the pike. Yeah, I'd have to go back and check docs to see what else is recent and near. I have all kinds of plans and hopes, things I'd like to do, but I don't want to overpromise, as some of those things may be a little further away.
Are you ever going to support SQL?
That'd be nice. I'd love to support SQL. We actually have a plan for how we might do something like that, but to date, no one has succeeded in running SQL on a graph. So instead, they create different graph query languages, but we think we've got a beat on it.
I'll be interested to see that too. So yeah, you posted. What are your what's the progress been made with aggregations with graphs? It's been kind of a bit of a sore point for some graph databases so far.
Yeah, so Quine has some built-in functions for that are not really available in other systems, and it kind of comes from this notion that we think of Quine, we call it a streaming graph, and it's really deliberately because it's not trying to be a database. It really behaves a lot like a database, stores data, queries it, all that kind of stuff. But the streaming side is really where we're trying to lean, and that includes. I'm trying to think of a good way to show this. Is this here? Nope. Oh, that's why it's this. All right, now, is it a function or a procedure? I just forget off the top of my head. Oh, procedure. All right, so I'm telling Quine to list out all of its capabilities and functions here. We can do some things under the hood, like this increment counter functionality. So when aggregating in a graph, a node is essentially a place to hold data. And different things in the graph can cause certain events to occur that you might want to start aggregating some results for, like count how many times something like that has occurred. And so we've built some custom functionality like this increment counter functionality that takes a node and a property, and it will go atomically increment that particular counter as, just kind of a simple example of an aggregation. There's some other functionality as well, kind of being built in, like reifying time, and for working with time series data, and rolling up questions like how often do certain patterns occur within certain time windows, time boundaries. And so choosing data models to represent where that data gets stored, or what defines how your aggregation is going to be computed. Those are I guess kind of some emerging functionality being included in Quine right now. But they also might be examples, like at the extreme end of that spectrum, they might be examples of where you wouldn't want to use Quine. So if you're trying to do something that is, stream data in, build it all up, and then tell me the moving average, of all the data that is coming through, that sort of an aggregation, which would or even just a general average, like you have to compute something over the entire data set, to roll up a computation that is the aggregated result of what you're trying to find. That's probably an example of something you wouldn't want to use Quine for, or where there's no real advantage for using Quine, because you'd still have to go iterate through a whole column of data to compute that result.
Thanks.
Would it make sense to just jump to the native database, and run the query in that case?
Yep, you certainly could.
Well, cool. I guess to kind of close it out, for people who want to learn more about Quine, thatDot, you, Ryan, anything else, how would they do that?
You could check out quine.io. Right here, you'll find just kind of introductory material, and then hopefully lots of good docs and getting started information on how to play with it. You'll find recipes there. thatDot is the company behind Quine, and so thatDot.com has some more information on what we can do with Quine, including some of the open positions that we're hiring for, like distributed systems engineer. So if any of this stuff is fun for you and you'd like to work on it full time, drop us a line. We'd love to talk. You can find us and learn more there, and hopefully just try it out. Let us know what experience you have. Here's a link up here in the top right to the Slack community. So if you have any questions or want to share your experience, by all means, drop in and send us a line.
Awesome. Thanks, Ryan. Much appreciated. So thanks to the audience for the great questions. I'll stop recording. This will be posted hopefully tomorrow to YouTube. So thanks again.